Welcome to the topic of Introduction to Scientific Data Visualization and Analytics. What is visualization? Visualization is a process of transforming numerical data to images. An important goal of visualization is to extract information from the data, which is typically called data analytics. Because we are using visual images to perform the task of data analytics, it is also called visual analytics. Visualization involves many sub-areas in computer science, statistics, and computational sciences. The core of visualization is computer graphics because the output of visualization is images. The information we extract from data typically have a form of geometry, so geometric and topological analysis plays an important role in visualization. Also, visualization is to allow the user to explore the data. So interface is very important when it comes down to the final product of visualization software. And this falls into the area of human-computer interaction, or HCI. To extract trend or aggregate information from the data before we perform any kind of visualization, oftentimes people need to apply statistical operators. For example, you often need to know the mean, the standard deviation, or even higher order moments of the data. When the size of data is very big, we need to use paracomputer clusters, also machines that have large amount of disk space. So high performance computing is very important for large-scale data analysis and visualization. To manage the data, we need to use databases. Also, we need to use data mining or machine learning techniques to classify or extract features from the data. And finally, we have computational sciences, which are the driving force of scientific visualization. So now let's look at a typical visualization pipeline. Starting from data acquisition or generation, we need to go through a sequence of steps. For example, we might need to prepare the data in case the data needs to be resampled or need to be denoised. Then before we can generate any useful images, we need to, first of all, extract features that are important to the user. And also, we need to map the feature, that it be geometry or images, to a visual output. We call that visual mapping. And we're going to analyze the result. Notice that I have a double arrow here, which means feature extraction, visual mapping, and the analysis are going to be done iteratively. In addition to analysis, we need to perform rendering, which is the topic of computer graphics. And finally, the rendering generates images or animations. From this output, we might need to go back to redo the data acquisition or preparation or any of the steps in this visualization pipeline. Now let's look at some of the steps in more detail. So the first step in the visualization pipeline is the data acquisition or generation. The type of data that typically are handled by visualization include spatial data, for example, the data from medical imaging or numerical simulations. And also the data can be collected from sensors. Examples are including radar or LiDAR data. Those are called spatial data because those data were collected from some spatial points, so inherently they are defined in space. In contrast, sometimes the data we need to visualize are non-spatial data, meaning they don't have inherently spatial properties. Examples are network data, and for example, graphs and trees, they are abstract concepts. Or text data, the paper, the books you're reading, they are documents, they do not have spatial property. Also in business, a lot of time we have tables. Here we call them matrix data. They are represented in spreadsheets. For non-spatial data, the goal of visualization is to map some spatial properties to the data such that we can display on the screen. Now, the type of data preparation needed strongly depends on the application. If the input raw data are represented as a sequence of basis functions, then we may need to perform some reconstruction to get data at the desired resolution. Also, sometimes the input data are noisy, so we need to perform denoising before visualization of good quality can be produced. There are also other type of preparation which may be needed, for example, resampling to a high resolution, transform or compress the data, or maybe the data are defined in higher dimensional space which are difficult to visualize, then we need to perform projection to lower dimension space. If the data is too big, a lot of time we can only process one chunk at a time. In that case, we need to perform partitioning. Sometimes it is called breaking. In order to allow the user to freely zoom in and zoom out the data, regardless of the size, then we might want to perform multi-resolution processing so that we can have better interactive speed. And finally, if we need to perform the visualization using parallel machine, then we have to worry about data distribution. And also, we have to consider the best layout to store the data in a file. A lot of time, it is difficult to visualize the data directly. And also, the user might be only interested in some specific features. So feature extraction is a necessary step in the whole visualization pipeline. Typically, we can have generic features, such as isosurfaces. For vector data, we can compute streamlines. Also, the user may want to find critical points, which represent, for example, the point that has local minima or maxima scalar values. Besides generic features, the scientists may want to find some specific feature that depend on the domain. For example, for computational fluid dynamics or CFD data, the scientists may want to find vortices, flow separations. For medical imaging or for material science, the user may be interested in the boundary between different materials, etc. This slide just to show where we are right now. So after we extract features, the next step is to perform visual mapping and rendering, which is a process of converting data or features of different kind to visual images or visual forms. Examples that we have in scientific visualization pipelines are volume rendering, which is a direct projection of three-dimensional data to image plane. If the feature is represented as geometry, for example, polygon, then we use GPUs or graphics hardware to perform polygon rendering. Or we can use some more expensive but high-quality rendering algorithms such as ray tracing and apply advanced illumination or stylized rendering to enhance the quality of the output images. Illumination can a lot of time enhance 3D depth cues, and stylized rendering can allow the user to focus on only important features. So we're getting close to the end of visualization pipeline. Let's look at the analysis. So the goal of analysis is to extract or prioritize features and raw data. Remember, we say the goal of visualization is not just the images. Actually, the user wants to retrieve information from the data. So important step for visualization is to perform analytics or analysis. Because oftentimes the output of visualization has the form of geometry or images. So the kind of analysis involved in visualization can be topological, such as we figured out the surface topology or vector field topology of the data. It could be geometric, that is, compute the curvatures or different fundamental forms to analyzing geometry so that we can differentiate more interesting places from ordinary places. If we only focus on the data, not the spatial form, then we can perform statistical analysis to get distribution, to compute entropy, or we can compute first, second, or higher order moments of the statistics. Finally, the last step, the output of visualization, is often the image or animation. The quality of the image is deeply affected by the visualization algorithm, and more importantly, the parameters chosen by the user. So you can see that sometimes we will produce better images, and sometimes we will produce something that is not very useful. People in the past have developed different metrics to evaluate the effectiveness of the images. The purpose of the analysis is to go back to tune the visualization algorithm parameters so that we can generate better images. Also, people utilize the property of images, such as the visibility, the object size, to optimize the visualization algorithm speed. One example is that if objects that are very small, then you can use a lower resolution representation so that you can improve the computational speed. So this is the entire visualization pipeline, which is the main focus of the course for this semester. From now on, we are going to focus on different stages of the visualization pipeline. In each stage, I'm going to give you more detailed information.